Let's do a quick example by leveraging on what we have learned through the previous two examples. In this case, what I want to consider is again a series of two reactors in which now a second order reaction takes place, right? The reaction is still A going to B, but now it is a second order reaction. So the rate of the reaction is equal to K multiplied by Ca squared. We assume there are no temperature effects, and we assume that the density is the same for all streams. Now, as you can see in the figure, we also assume there is a recycle stream that comes out from the exit stream of the second reactor and recycling back into reactor 1. So there is a recycle in this particular case. And the other difference is that we are not assuming that the volumes of the tanks are constant. We have not made the assumption that the volumes of the contents in the tank 1 as well as in tank 2 or reactor 1 and reactor 2, they are not kept constant. So V1 and V2, those could change. V1 and V2 are the volumes of the two reactors respectively. So the fresh feed is coming in with QA1 flow rate, and CAF is the feed concentration. Now out of the reactor, the volumetric flow rate is Q2 in the usual units, and the concentration is Ca1 in the exit stream. We know that because this concentration in the exit stream of reactor 1 is marked as Ca1, the concentration inside reactor 1 should also be Ca1, because we assume that the reactors are well mixed. So it's all homogeneous, and therefore the concentration of the exit stream will be the same as the concentration of what is inside the reactor. Now, this Q2 stream with concentration of Ca1 flows out of the first reactor and enters the second reactor, whose volume is V2 at any point in time. That's the symbol. Again, it is a well mixed tank. So what comes out of that reactor is indicated as Ca2 here. That's the product stream that is drawn out with a volumetric flow rate of Q3. So since this is Ca2, we assume there are no delays in the pipe, etc. Right? We assume fairly short pipes. And therefore, the concentration here is going to be Ca2, as well as the concentration inside the vessel should be Ca2, because what comes out of the reactor 2 is from what is inside reactor 2. So if Ca2 is the concentration of the product stream from the reactor, then Ca2 should be the concentration of A inside the second reactor. And the flow rate out of the second reactor at this point should be Q3 plus Q4, out of which Q3 is drawn out as the product and Q4 is recycled back. So the concentration of this stream is going to be Ca2, because this concentration should be the same as this concentration should be the same as this concentration. So all of these should be Ca2. So with all these inferences, we can kind of get this situation where all the labels are there, right? So now we are ready to write the balances, the mass balances. We don't bother about energy balance here because we assume no temperature effects. Since we have two species, A and B, we have to write two balances for each reactor. Now, we can write an overall balance for reactor 1 and species balance for species A for reactor 1. We can write an overall mass balance for reactor 2 and species A balance for reactor 2. That is the principle we'll adopt here. On the alternative, we can write species balance for A, species balance for B for reactor 1, and species balance A and species balance B for reactor 2. That's also fine. In any case, we will have 4 equations. Now, we can say since the volume of reactor 1 is allowed to be dynamic, that means V1 is not constant, the rate of change of volume in reactor 1, which is indicated by dV1 by dt, should be equal to the net volumetric flow rate in minus the net volumetric flow rate out. So the net volumetric flow rate in is going to be Q1 plus Q4. Out of reactor 1, this is reactor 1, right? Out of reactor 1, the volumetric flow rate out is Q2. So since it is outflow, you get a minus sign. So the rate of change of volume for reactor 1 is dV1 by dt, and that's going to be equal to Q1 plus Q4 minus Q2. The units of Q1, Q4, and Q2 are typically in meters cube per minute, and volume is in meter cube and time is in minutes. So the left hand side will have units of meter cube per minute as well. So everything is fine. For the second reactor, the inflow volumetric flow rate is Q2. The outflow volumetric flow rate out of reactor 2 at this particular point is going to be Q3 plus Q4. Therefore, inflow rate is Q2, outflow rate is Q3 plus Q4. So inflow minus outflow. That imbalance will lead to changes in volume contents for reactor vessel 2. So dV2 by dt is going to be equal to Q2 minus brackets open Q3 plus Q4 brackets close, or Q2 minus Q3 minus Q4. So this completes the overall mass balance for reactors 1 and 2. And we are able to write it in terms of these volumes and volumetric flow rates simply because we assume the density to be the same for all streams. That makes things a bit easier. If that is not true, if the densities are all different, we can modify this equation suitably. It's not going to be too complicated, but certainly assuming the same density for all streams makes it much better. When we go for the component balances for species A in reactor 1, we get what you see on the left hand side, very much like what we have done in the earlier two examples. Here we acknowledge the fact that the volume is not constant. So we cannot take the volume out of d by dt term because V1 is not constant. In the previous two examples, the volume of reactors were assumed to be constant, and therefore we could write V dCA by dt. Here, since the volume is also changing with respect to time, we will just not pull it out of the derivative term. So we will say d by dt of V1 CA1. V1 is the volume of the first reactor. CA1 is the concentration of A in the first reactor. So this should make sense to us. So this is going to be equal to the net A coming into the reactor 1. So it is going to be coming from two sources, from the fresh feed stream and from the recycle stream. So you have Q1 CAF, that is the amount of A coming through the fresh feed stream. Then plus, because there is another inflow stream for A, so plus Q4 CA2, Q4 times CA2. A, unreacted A would leave through the exit stream from reactor 1. So the stream has a volumetric flow rate of Q2, and we have the concentration of that stream to be CA1. Therefore, this is the amount of A leaving reactor 1 and into reactor 2. And then some of A is going to be destroyed by the reaction because A becomes B, right? So there is some amount of A that gets depleted due to the reaction. So that amount is going to be with a negative sign because A is lost. So we have this negative sign, and reaction rate multiplied by the volume. So here the volume is V1 because we are talking about reactor 1. And the rate of reaction is going to be K CA1 squared because we assume second order kinetics. And in this reactor, the concentration of A is CA1. Therefore, the reaction rate in the first reactor is going to be KCA1 squared. So this gives us this equation for reactor 1 species A balance. Now, when you come to reactor 2, what you see is, of course, similar things with appropriate symbols is on the left hand side. So we say d by dt of V2CA2. V2 is the volume of the second reactor at any point in time. CA2 is the concentration of A in reactor 2 at any point in time. Those are the symbols we have used for volume and concentrations. So d by dt of V2CA2, that is going to be equal to the inflow of A into the second reactor, which is going to be Q2 times CA1, minus the outflow of A from the second reactor. So the outflow volumetric flow rate is Q3 plus Q4. That's the volumetric flow rate. The concentration at this point is also Ca2, right? So minus Q3 plus Q4 Ca2. This is the amount of A exiting here, right here at this particular point. And some amount of A has been lost due to the reaction that continues in reactor 2. A going to B still happens in the second reactor. So the volume is V2 in the second reactor, and the reaction rate is Kca squared. It's a second order reaction as stated earlier, but the concentration of A is Ca2 in the second reactor. Therefore, the rate of the reaction is going to be equal to Kca2 squared. Remember, the rate of the reaction is always in moles of A, because we are talking about species A, per meter cube per minute. And when you multiply it with volume, which has got units of meter cube, you're going to get moles of A per minute. This term, right, each of the terms on the right hand side, Q2CA1, right, Q2 is going to be in meter cube per minute. CA1 is going to be in moles of A per meter cube. So if you multiply the two, meter cube and meter cube cancels, leaving you with moles of A per minute. So all the terms, you can verify that all the terms in the right hand side as well as on the left hand side will have units of moles of A per minute. Therefore, it is fantastic. You could do the same thing for reactor 1 species A balance as well to verify whether the units is correct. So if you look at the four equations we have written, right? So these two equations for the overall balance and these two equations for the species A balance complete the mathematical model for the system. Please note that d by dt of Vc can be written as V dc by dt plus C dV by dt. This is using the chain rule in calculus, or the product rule if you like. So we would just use this, and this d by dt of V2 Ca2 can be written as V2 d by dt of Ca2 plus Ca2 dV2 by dt. And we have dV2 by dt here. So you can do the substitutions, simplifications, etc. if you want to handle that. I hope this example has been a good learning experience for you, and this may be very useful as you try to solve problem 2 in your assignment. Thank you for your time.